Okay, what we're looking at is a Micronta 28 range FET multi-tester. It'll measure resistance, DC voltage, AC voltage, and amperage. Multimeter, more or less. It's got, on the DC side, the FETs give you a 10 megohm input impedance, which is excellent for isolation and works quite well for a number of other things that I'll get into. We have 10 kilo ohm per volt AC measurement, and we are able to read DC amperage from 100 microamps on full scale up to 300 milliamps, and then we have a shunt input that'll allow us to read up to 10 amps. We can read our DC voltage from 0.3 volts up to 300 volts full scale, and we do that in 8 ranges, and we have 5 ranges of resistance from times 1 through times a million, and then we have a graduated scale, but let's say 10 ohms to 10 megohms. I mean, that would be half scale. That would be a good reading. Now what I'm going to do, I'm going to zoom in on the lens and hope that that allows you to see the needle, which is relatively fine and yet still read the scale as I take you through this, and I'm going to describe then what I'm doing. We have an AC standard and a DC standard setting up here on the bench. The big black banded thing is the AC standard, and the unit above it is our DC standard. We're going to use those to provide the voltages that we will be measuring on this. And then we have a resistostat resistance box. It's accurate to 0.001%, excuse me, on each of its ranges. So we'll use that to check the resistance. Okay, let's go ahead and zoom in on this meter and see what we can do here. We are going to start with our AC voltage. Let's start on the 300 volt range. First thing you want to do is you want to zero the meter. Every range you're going to be zeroing, and I'm going to do that. There's a parallax mirror behind on the rear scale. You line the reflection in the mirror up with the actual needle, and then that eliminates the parallax, and you're looking perpendicular to the scale, and that's exactly where you want to be. So like right now I'm doing that, and I'm going to adjust for 0, and that puts me at 0 right there. Okay, and then and we're going to go ahead and turn our AC standard on, and we're on the 300 volt range. So the first thing I'm going to hit is 100 volts. And we see the needle rise up to the 1 on the lower third of the scale. You're more accurate when you get on the upper 2/3 of the scale, and you lose accuracy as you drop down to the bottom. It's just one of the facts about an analog meter. I'm not going to go higher in AC voltage, but I will change our scale and we'll go down. And let's we're reading about 98 volts here. Let's take ourselves down. There's 90. That's dead on. 80. That's dead on. 70. There we go. 60. Looks good. 50. 40, 30, we're starting to drop off on the low end. Let's go ahead and change scales again. Alright, we're on the 30 volt scale. We have 30 volts coming in, and we are reading 30 volts on the lower part of the scale here. So that looks good. Let's go 20. Alright, here's the 2. We're at 20. And 10. And we are right on the 10. Looks excellent. Let's go ahead and we're going to go down to the 3 volt scale. Let's change our volt scale. Let's check our 0 again. Alright, our 0 is a little bit different. There we go. It's 1, 2. 2 is dead on. 3. 3, we're just a hair high on 3. Okay, and let's go ahead and we're going to change now to our DC voltages, and we'll check those. Give me a moment. Okay, we've got ourselves zeroed on the 0.3 volt DC input. We've got 1 volt, excuse me, we got 0.1 volts coming in, and we see ourselves rise just a hair under the under the 1 volt line. Let's go ahead and go to 2. Got 2 dead on. 3. Just a hair high. There's 3 dead on. Okay. Let's change scales. We're going to go to the 1 volt scale. We're reading on the top here, and we have 0.3 volts coming in. Alright. Let's go ahead and go to 0.6. 0.6 is dead on. 9. 0.9 looks good. And 1 looks good. Okay, let's go to the 3 volt scale. We're back down to a 1. There's 2. 2 is dead on. 3. 3 is dead on. Well, I took care of the 0. Alright, let's go ahead and hit the 10 volt scale. There's 3. We're right on the 3. 4. 5. 6. 7. 8. 9. And then let's go to the 30-volt scale. And at 30 we have 10 volts coming in. We're just, yep, we hit the 1, 2, yep, 3. Alright. Go to the 100-volt scale. We're on the top. There's 30 volts, 50 volts, 80 volts, 90, 100. Okay. That does it for the DC range. We're going to go ahead and take a look at the ohms. Bear with me. Alright, we're on the ohm scale. We are zeroed and we're getting ready to put on 1 ohm. We've zeroed and spanned. There's 1. 2 ohms. 3 ohms. 4. 5. 6. 7. 8. 9. 10. Alright, let's go ahead and get ourselves back down to 0 and go to the next. There's our 10, 20, 30, 40, and we're going to get less accurate as we go up, so 50. Let's go ahead and change our range. Go to the times 10 range. Once again, we got a 0. We got a span. All right. We're zeroed. We're on the times 10 range. We're putting in 10 ohms. We're getting 1. 20 ohms, we're getting 2. 2 times 10 is 20. 30 ohms, we're getting 3. 3 times 10 is 30. 40 ohms, we're getting 4. 50 ohms, we're getting 5. 6, 7, 8, 9, 10. That would be 100 ohms, 10 times 10. Times 10 is 100. Okay. 20 times 10 is 200. 30 times 10 is 300. 40 times 4. 50 times 10 is 500. 600. 700. 800. 900. There would be 1,000. Down to 0. Let's go to 1,000 ohms. Alright, we're zeroed. We're going to go to 1,000. There's 1, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. 10,000, 20,000, 30,000, 40, 50,000, 80, 90. There's 100,000. Going to the 10,000 times 10,000 range. No, I don't want that. Here's 10,000, 20,000. 30,000, 40,000, 50,000, 60, 70, 80, 90, 100,000. Okay. There's 100, 200, 300, 400, 500, and 100,000. Going to the times 1 million range. And here we're going to need to use some calibrating resistors, because the best I can do with this is 1 million. So there's a million right there. Let's get a 10 million ohm resistor. Right on the money. And that concludes the resistance. Okay, well, we've connected the Micronta to a series of precision resistors with a cooling fan. It's my load box. Each one of the resistors is better than 1%. Most of them are like 0.1%. And right now we've got a 100 ohm resistor as a load. We're going to feed from a power supply in through this series, through this resistor in series, then in through the current meter. And we're going to observe the reaction on the current meter to different voltages on the power supply. So if you'll bear with me here, we'll give it a go. I'm going to try and manage to do a couple of things at once. Alright. So right now, I'm going to start turning up my voltage. Alright, we've got 10 volts coming through a 100 ohm resistor, precision resistor. We are on the 300 mil range, which would put us on the 3 range here, and we see that we are 1/3 of the way up at 1 on the range, which would be 100 mils, 100 milliamps, which would be right because we have 10 volts across 100 ohms. That'd be 100 milliamps. We can momentarily take her up. We'll take her up to 2. Alright, and we have 20 volts. And we are actually pushing just a hair greater than 2. Maybe our 0. We'll check our 0 and be sure. Alright, let's try it again. And just about perfectly on 2 with the 0 redone. Okay. So we're good there. Let's take this back down. Let's go to the 30 mil range. All right. Check our 0. Our 0 is off. Let's see. Get it adjusted here. Every time you change range, you got to change 0. That should do it. All right. Go back in again. Let's go ahead and give her some voltage. Looks like we have 1.1 volts, and we're getting 10 milliamps on the meter right now. All right, let's take her down a little further. We're going to go to the 3 mil range, and I think to do this, I think I'm going to raise my my resistance. I'm going to go to the 1000 ohm. Looks like 3 mils to me. 3 mils looks good. We're running about 3.2 volts over 1000 ohms. Approximately 3 mils. We're getting a little bit of meter error here. You're picking up some resistance in the meter because of the low range, but it's still good. And then finally, let's go to the 100 microamp range. Okay, now we've used a 10,000 ohm 0.1% resistor in series. We're on the 100 microamp range, so that's the most sensitive range. But the meter resistance is going to come to play here. So it took 1.3 volts going through that 10,000 ohm resistor to produce 100 microamps of current according to this meter. And I'm looking at the voltage drop across that 10,000 ohms, and I see it's 1.00, so essentially a volt. So 1 volt across 10,000, and that's going to give you 100 microamps. So I'm providing the proper current, I'm reading the proper current. It takes a little bit more voltage out of my power supply because I have to overcome some internal resistance in the meter, but that's our most sensitive scale, and we've proven that current reads. So DC voltage, AC voltage, current, ohms, it all functions. So okay, why would I want to have an analog meter when I could have a digital meter like I do have on my bench? I mean, after all, a digital meter does give you greater precision and accuracy, does it not? Well, the answer is yeah, it does. That's why our technology has shifted mostly that direction. However, the usage of a digital meter in every instance isn't the perfect choice. I can give you one specific instance, and that's if I was to say peaking. When you want to peak something, you're observing a change in some circuit parameter. As you're making an adjustment, you're observing a change. If you're looking at a digital meter, you're going to see numbers fluctuating all around. Let's demonstrate that. Alright, I have both the analog meter and the digital meter connected in parallel, reading the voltage from this adjustable power supply. Now I'm going to pretend that that power supply is a tuning circuit. I'm going to tune the IF stage of a shortwave radio, trying to peak it out. I mean, that would be, as I adjust my IF stage, my voltage is going to increase or decrease depending on whether or not I'm adjusting my IF to the center frequency and getting it in tune. So let's go ahead and do this. I want you to observe both needle and digital to see what I'm talking about. It's real easy for me to see that needle hit its peak and come back down again, but I gotta wait for those digits to fluctuate and change, and I have to read them in my head and kind of average them. Not so with that meter. I can see exactly what I'm doing. Now, it's not to say that you can't peak with a digital meter. It's just harder. I think you're going to be a lot happier doing a peaking job with an analog. My preference. Okay, that's one thing. This meter also has a 10 megohm per volt input resistance because of the FET and its input stage. What's good about that is that you can couple that with a device like this probe, This is a Fluke 85 RF. This kind of a probe will work with a 10 megohm input, and in the tip of the probe you have a germanium diode and some capacitors that form a filter circuit in such a way that the voltage that's detected is turned from AC into DC, and the filtered result is the RMS average of the radio frequency. So I can read a radio frequency with this on this meter from 100 kilohertz up to 500 megahertz, and it'll read it anywhere from 1/4 of a volt output to 30 volts RMS. So this can be turned into a fairly sophisticated RF meter. Not a millivolt probe. I can't read millivolts with it. I have to have 1/4 of a volt to overcome the diode that's in the circuit. But as long as I have 1/4 of a volt of RF energy, this thing will work. So I can use it to adjust and measure the output on my generators and make sure that my analog meters are reading appropriately. Can use it with my my standards, my 10 megahertz standards, whatever I would have need of. So there's another good reason to have this kind of a meter. So okay, happy bidding. Along with it, you'll get the original user manual with the schematic diagram in it. It came in handy for me. The fellow who sold me this unit failed to mention that he burned out 3 of the ranges and I had to do extensive repair on it. But I did good repair and it's working well. Comes in the original box. It's in excellent shape. Repaired the handle. But the only thing that's worn at all is a little bit of the faceplate down here is scraped away for some reason, but it doesn't. It's not even on the digits. It's just plastic or paint on the plastic. So happy bidding. Thank you for listening. Bye.